In this lesson, we will study techniques for calculating limits. The following rules are often helpful when evaluating limits, and there will be more rules as we go forward in the lesson. I'd like to explain each one of these rules for us before we actually use them to evaluate some limits. You may want to pause the video here, copy down the rules, and then press play again on the video. That way you can listen to the explanation. The first is the constant function rule. It says the limit of constant k as x approaches a is k. Now, in the constant function rule, this is a constant function, right? So f of x is equal to k. F of x is equal to k. It's a constant. So it always has the same value, k. I mean, think of it as the graphical representation of a constant function is a horizontal line, right? The values of this constant function are always the same. They're always k. So however close you get to allowing your x values to approach a, the function values are never changing. They're always k. So in this constant function rule, the constant function k always has the same value, which is k. So I hope that makes sense for you. Here's a picture that I just quickly sketched for us, just in case someone may understand better by looking at a picture. The graph of a constant function is a horizontal line. So I drew a horizontal line going right through the value of k on the y-axis here. So this is the graph of the constant function f of x is equal to k. All right, so now I want you to notice that as x values approach a on the left, and as x values approach a from the right, the function value is always k. The function value is always k. No matter how close you get to a on either side, the function values are never changing. The function values are always k. That's why the limit of k as x approaches a is k. Next is the identity function rule. The limit of x as x approaches a is equal to a. Now, in the identity function rule here, the value of the identity at x is the same as x. Here I'm drawing a quick sketch, a very quick sketch of the identity function for us. It is a line going right through the origin whose slope is 1. Notice that the point 1, 1 is on the graph. The point 2, 2 is on the graph. The point 0, 0 is on the graph. And I think you notice the pattern. 3, 3 will be on the graph. -1, -1 will be on the graph, right? So notice, like, for example, let's take 1, for example. As x values approach 1 on either side, as x values approach 1 on either side, the function values are approaching 1. As x values approach 2 on either side, the function values are approaching 2, right? So as x values approach 1, the function values approach 1. As x values approach 2, the function values approach 2. And that is because this is the identity function. So the limit of the identity function x as x values approach a will just be equal to a. I hope drawing a sketch here, even though it's a rough sketch, I hope it helps. Okay, the sum and difference rules, and I apologize for my sloppy writing. The limit of f of x plus or minus g of x, so this is either a sum or a difference of two functions here, and we are assuming here that the limit of f of x exists and the limit of g of x exists. So we're taking the limit of a sum of functions or a difference of functions as x approaches a. This is equivalent to the limit of f of x as x approaches a plus or minus the limit of g of x as x approaches a. And quickly finishing this off, the product rule, you have a product of functions here, And again, we're assuming that the limit of f of x exists, the limit of g of x exists. So we have the limit of the product of our two functions as x approaches a is equal to the limit of f of x times the limit of g of x as x approaches a, of course. Finally, the limit of f of x divided by g of x as x approaches a is equal to the limit of f of x divided by the limit of g of x, and each of these as x approaches a. So I want us to practice using some of these rules to evaluate some limits. So let's have some fun. Here we go. All right, here we go. Finding a limit of a linear function. So 3 plus 2x is a linear function. Just FYI, it's a linear function whose graph is a line with a positive 2 slope and whose y-intercept is 3. So I guess I explain the graph, or I'm trying to give you a visual representation of the graph, so that way if you would like to go about finding this limit by drawing the graph, by sketching the graph, you could do that as well. But I'm going to practice using these rules for limits. All right, so the first thing I'm going to do is I want us to realize that we can write this as, I'm not sure I finished reading this, the limit of 3 plus 2x as x approaches 4. The limit of 3 plus 2x as x approaches 4. The first thing I can do is I can use the sum rule to basically break this up and say this is equivalent to the limit, I'm writing limit in cursive there, as x approaches 4 of 3, and then plus the limit as x approaches 4, I've got the 4 over here, of 2x. So notice that I'm taking the limit of the first term and then plus the limit of the second term. The sum rule that we wrote down, I guess that's the third rule that we wrote down earlier, allowed me to do that. Now, notice that this is a constant. And the constant rule says that the limit of this constant, which is 3, as x approaches 4, is 3, right? And then here I can use the product rule to say that this is the limit as x approaches 4 of 2 times the limit as x approaches 4 of x. That's the product rule. Now, notice that this is a constant again, so the limit of 2 as x approaches 4 would just be 2. And then this is the identity function. The limit as x, the limit of x as x approaches 4 will be 4. So I'm going to go ahead and use the constant rule and the identity function rule. So now I have 3 plus 2 times 4. And when you evaluate all of this, let's see, 2 times 4 is 8, plus 3 is 11. So this is the limit. This is the answer. The limit of this linear function as x approaches 4 is 11. If you were to graph this line and then look at the graph and inspect or look closely as x values approach 4 from the left and from the right, you should see that your function values are approaching 11. That was fun. Now, I do want you to see something. Plug in 4 into this linear function, just from the very beginning. 2 times 4 is 8, and 8 plus 3 is 11. That's it. So what I really want you to see is that for any linear function, I should write this down for you. I will. For any linear function, the limit of that linear function as x approaches a, let's just a, you can just actually plug that value into your linear function. Let's add that to our notes. All right, I wrote it out for us here. For any linear function, f of x equal to mx plus b, that's slope-intercept form, the limit of that linear function as x approaches a is simply f of a. Again, I can show you this, but I mean, you just saw it in the previous example. This can be broken up right here, m times x as a product, and this is a constant, and so you can use your product and constant rules here and your sum rule to show that this is always true. Cool. Let's move on. The next example I'm going to have us consider is finding a limit of a polynomial function with one term. Let's check it out. We have the limit of this polynomial function. It's a monomial because it's one term, and it's degree 2, so it's quadratic. So it's a quadratic monomial. At the end of the day, it's a polynomial function. There's one term only. For anyone that wants to explore the graphical approach, you would graph this quadratic polynomial, which of course we know is going to be, or it is a parabola, and it's a parabola going upward, right? Because the leading coefficient is positive. So you can actually graph this parabola going upward and look at how your function values are changing as x gets infinitely close to 5 on both sides. Okay? We're about to use our rules instead. As you can probably imagine, our rules will be probably a lot faster in evaluating the limit as opposed to, or when compared to graphing the parabola. Here we go. The first thing we can do is we can rewrite this as the limit of 3 as x approaches 5. I'm trying to write neater here, times the limit of x squared as x approaches 5. Which rule would allow us to do that? The product rule, that's right. Now, the constant rule will tell me that the limit of 3 as x approaches 5 is 3, right? Because a constant function is always equal to that value. So this is 3 times, and then what I can do here is I can rewrite this as the limit as x approaches 5, right? Of x times the limit as x approaches 5 of x. Because after all, x squared is equal to x times x. This is the product rule. Now, each of these are identity functions. So the limit for each one of them, the limit of x as x approaches 5 will just be 5. So this is going to be 5 times 5, and that's by the identity function rule. So this is 3 times 5 times 5, which is equal to 75. This is the limit. Isn't that great? Hey, I want you to notice that had we just plugged 5 in from the very beginning, 5 squared is 25, and 25 times 3 is 75. So I hope that you're seeing that it would have been a lot faster had we known that from the beginning, that all you got to do is plug 5 in. The reason why that works so neatly, so nicely, is because polynomial functions are continuous, because they are continuous. By the way, a linear function is a type of polynomial function, right? A linear function that we just looked at previously is a polynomial function of first degree. So what we're saying about polynomial functions in this example applies to the previous example as well. All right, let's look at another one. This time, let's look at finding a limit of a polynomial function that has more than one term. All right, finding a limit of a polynomial function. This polynomial function happens to be a cubic trinomial. Cubic because it's degree 3, trinomial because there's 3 terms. You can use your earlier studies of polynomial functions to graph this polynomial function. That might take a while. You're going to have to find the zeros of the polynomial. You can use things like the rational zeros theorem and Descartes' rule of signs and the boundedness theorem and synthetic division and all of those useful tools and theorems to find the zeros of this polynomial function and sketch its graph, find its intercepts, and then you can look at the graph and see what's happening to your function values as x values approach 2 on both sides. That might take you some time, but it would be a lot of fun. here in this lesson, we're focusing on using the rules. So here we go. What we're going to do first is we're going to use the difference and the sum rules to break this up. So we're going to say the limit of 4x cubed and then minus the limit of 6x, I forgot, as x approaches 2, plus the limit of 1 as x approaches 2. All right? So here we have a polynomial of just one term, and we just saw in the previous example that a fast way of evaluating a polynomial, evaluating the limit of a polynomial of one term, is to just go ahead and plug 2 in. So that's what you're going to see me do here. This here is a polynomial of one term as well. It actually happens to be, you can say it's a linear function. It's a linear function. So you're going to see me just plug 2 in. And then this is a constant. So you're going to see that this is all equal to just 1. So here we go. So you're going to see me say 4 times 2 cubed. So I just plug 2 in. Minus 6 times 2. So I just plug 2 in. And then by the constant rule, that last limit is just 1. So what is this? 4 times 8, which is 32, minus 12, plus 1, right? All of this is equal to 21. 21 is the limit of this cubic polynomial function as x approaches 2. Now, make sure you have this because I'm going to erase some of the board here. And if you're not ready for me to erase the board, then just pause the video. Watch this. 4 times 2 cubed minus, 2 cubed minus 6 times 2 plus 1. If we would have just plugged 2 in from the very beginning, we just get 21. That's exactly what we did here by using the rules. If we would have just plugged 2 in from the very beginning, we would have gotten our limit. So what we're about to write down in our notes is that for any polynomial function, we can just evaluate the polynomial function at that value. We're going to call it a. This is what I wanted to add. Assuming that f of x is polynomial, the limit of a polynomial function as x approaches a is simply f of a. That is super helpful, everyone. Make sure you have this highlighted in your notes. It will save you a lot of time. All right, let's look at another kind of function. Okay, they want us to find the limit of a rational function. Now remember, by definition, a rational function is the quotient of two polynomials. So here, p of x and q of x are polynomials. That's what I've written here. They're polynomials. And of course, we don't want this undefined. So q of x is not equal to 0. Q of x is not equal to 0. All right, so we want to find this limit, okay? The limit of this rational function. This is a rational function as x approaches a. So here we go. We can say that this is equal to the limit of p of x as x approaches a divided by the limit of q of x as x approaches a. Now, this is one of the rules that we talked about in the beginning part of the lesson. This is the quotient rule, right? Now, don't forget that each one of these, p of x and q of x, each of these functions are polynomial. And we just said that whenever you evaluate the limit of a polynomial function, all you got to do is plug that value in to your function. So the numerator is simply p of a, and the denominator is simply q of a. Okay, that's the limit. That's what they're looking for. So if you have a rational function, just plug that value a into the function in the numerator and into the function in the denominator and evaluate. All right, what we want to do next is list out some more rules for evaluating limits. Now, some of these rules, we already have them written down in our notes, like I'm going to give you the polynomial function rule, the rational function rule, and we already have those kind of written down. But so it might seem a little redundant, but there will be some new rules as well. All right, so here we go. Okay, so we have some more rules here. The first one's called the polynomial function rule, then the rational function rule. We talked about these two already. Equal functions rule, power function rule, exponential function rule, and the logarithmic function rule. All right, so let's go for the first one, polynomial function rule. Here it is. Here we're assuming that p of x is a polynomial function. The limit of a polynomial function as x approaches a is simply p of a. We already had that. All right, let's move forward. Rational function rule. All right, here let f of x be a quotient of 2. So this is a division. This is a fraction bar. So it's a quotient of 2 polynomial functions. So p of x and q of x are polynomial functions. So let f of x be this rational function here. The limit of such a rational function as x approaches a is p of a over q of a. That's what we did in the previous example, okay? So basically plug that value a into the polynomial in the numerator and into the polynomial in the denominator. Here we must say that there's a condition, and that condition is q of x is not equal to 0. Because if q of x is equal to 0, this rational function is undefined. All right, next, equal functions rule. Now this is a new rule that we haven't seen yet. All right, if f of x is equal to g of x, right, if these two functions are equal, then their limits are equal as x approaches a. So the limit of f of x as x approaches a must be equal to the limit of g of x as x approaches a. Cool deal. All right, power function rule. This one's pretty cool. The limit of f of x to the power of k as x approaches a is equivalent to the limit of f of x as x approaches a raised to the power of k. So basically you can evaluate the limit of the function and then take that limit and raise it to the power of k. And here, k here is any real number k. Okay, that's a real number. So you can apply that power basically after finding the limit. Pretty cool. All right, this is the exponential function rule. So here we have the limit of b to the power of f of x, okay, as x approaches a. This looks like an exponential function, is equal to the base b raised to the power of the limit of f of x as x approaches a. Here we are assuming that b is a positive real number, right? B is a positive real number. So basically, we can say the base raised to the power of the limit of that exponent, the limit of that function that's the exponent. All right? Cool. Last one. And in order to create some more board space, I think I might erase some of this a little bit before writing the last rule. All right, here it is. The limit of this log function here is equal to log of the limit of f of x. Did you catch that? So here, I guess it's log base b of this function, and then limit of that, right? The limit of log base b of f of x is equivalent to log base b of the limit of that function as x approaches a. Now, what's going to be exciting is we're going to look at a list of examples in a few minutes here, or over the next few minutes, and we're going to be able to use some of these rules. So we're going to actually be able to see these rules in action. All right, so let's do it now. Okay, finding a limit of a square root function. This is going to be fun. The limit of the square root of 5x minus 1 as x approaches 2. Hey guys, don't forget that you can always graph this square root function and then look at how the function values are changing as x approaches 2 on both sides. Using the rules that we've been going over, this is equivalent to, this is equivalent to the limit as x approaches 2 of 5x minus 1, and then all of that raised to the power of 1/2, right? So a square root function can be rewritten using a rational exponent. Now, this follows from your rules from exponents that you probably learned in your algebra class. Now we can use the power function rule. This was rule number 9, to say that this is equivalent to the limit of 5x minus 1. Let's put that in parentheses, right, because it's more than one term, as x approaches 2. And then we can say all of this to the power of 1/2. That's what the power function rule said we could do. Now, notice that 5x minus 1 is a polynomial, the polynomial function. So we can simply plug 2 in. Now, when we plug 2 in, 5 times 2 is 10. 10 minus 1 is 9. So this is 9, and then raised to the power of 1/2. Now, again, the exponent of 1/2 is the same thing as the square root. So this is basically the square root of 9. So the evaluation of the limit is 3. Isn't that great? All right, finding a limit of an exponential function. All right, the limit of 3 raised to the power of x squared plus 1 as x approaches 2. Now notice that the exponent up here is a quadratic binomial. All right, so it is a function up here. Notice that your base, remember the condition on your base was that it had to be a positive real number, and 3 is a positive real number. Okay, so by the, the exponential function rule, which one was that? Number 8, rule number 8, we can say that this is equivalent to 3, right? That's the base, and that's a weird looking 3, but it's 3 raised to the power of the limit of x squared plus 1. That's more than one term, so let's keep that in parentheses there. Of course, this is as x approaches 2. Again, this is by the exponential function rule. Notice that this is a polynomial, right? So we can just plug 2 in. 2 squared is 4. 4 plus 1 is 5. So this exponent is just 5. So this simplifies to 3 raised to the 5th power. 3 times 3 times 3 times 3 times 3. 243 is the limit. Man, this is a lot of fun. Let's keep pushing forward. All right, next we have finding a limit of a logarithmic function. We got limit, or the limit of log of 3x to the 5th power plus 4 as x approaches 2. Hey, just as a quick reminder, the base of the logarithm is not written. That must mean it is 10. So this is a common log. Okay, the logarithmic function rule, which was rule number 11, okay, says that this is equivalent to, okay, log, base 10, right, of the limit of, oops, sorry, whoa, okay, let me keep it all one color here, sorry, there we go, log of the limit as x approaches 2 of 3x to the 5th power plus 4. Now, 3x to the 5th power plus 4, that is a quintic. Degree 5 is called quintic binomial. So this is a polynomial function of degree 5. We can just plug 2 in. When you plug 2 in, 2 to the 5th power times 3 and then plus 4, I believe all of that is 100. So then this is just log of 100. Now remember that the base of your logarithm is 10. We know that because it's not written. So a logarithm is an exponent. So it's asking you, to what exponent do you raise 10 to get 100? and that would have to be 2. So the limit is 2. Man, that was a blast. Cool. Let's look at maybe 1 or 2 more examples. All right, this one's going to be interesting. We have the limit of a rational function here. The limit of x squared plus 2x minus 3 over x squared minus 3x plus 2 as x approaches 1. Hey, I want you guys to notice that, this is equivalent to the limit as x approaches 1 let's go ahead and factor the numerator and the denominator. The factors of the numerator are x plus 3 times x minus 1. And if you factor the denominator, it's x minus 2 times x minus 1. I do want you to notice that the denominator becomes 0 if you let x be 1. Right? If you let x be 1, you get 1 minus 1, which is 0. The entire denominator becomes 0, and then the function, therefore, is undefined. So the rational function rule cannot be applied directly. It cannot be applied directly. But notice that what we can do here, because we have common factors, we can say that this is going to be equivalent to the limit as x approaches 1, right, of x plus 3 over x minus 2. Now, we have to say as long as x is not equal to 1, okay? What we're actually using here is the equal functions rule. That was rule number 8. To say that this given rational function, you have to make sure you catch this, okay? This given rational function is equivalent to or equal to this rational function as long as x is not 1, or when x is not 1. So this rational function is equal to this rational function when x is not 1. Because of that, we can say this limit will be equal to this limit. Okay? Now we can apply the rational functions rule directly. This is rule number 7. And we can just go ahead and plug 1 in. So this is going to be 1 plus 3 over 1 minus 2. This was a very important example. So what is this? 4 over negative 1. So then the limit is negative 4. All right, let's wrap up this lesson by looking at some of these rules here. These are limits involving trigonometric functions. Now, these limits here can be proven or obtained by using a geometric argument or by concepts covered in calculus. Okay, but you can use some geometric arguments to derive the following rules. The limit of sine of x as x approaches 0 is 0. The limit of cosine of x as x approaches 0 is 1. And the limit of sine of x divided by x as x approaches 0 is 1. Let me give you one more. This one's interesting. Limit of cosine of x minus 1 over x as x approaches 0 is 0. All right, these are some really, really helpful limit rules involving trig functions. Let's use one of them now, and then maybe we can end the lesson after that, okay? Okay, folks, last example. It's finding a limit of a trigonometric function. Find the limit of tangent of x over x as x approaches 0. Now, we don't have a rule explicitly here for tangent of x over x, but I think with some manipulation and some identities from our trig studies, we can actually figure this out. All right. So what we can say is this is equivalent to the limit, right, as x approaches 0, okay, of 1 over x times tangent of x. Now, this is the product rule for limits here, okay? And then what we can do next is we can say, well, this is equivalent to the limit as x approaches 0 of 1 over x times, now tangent of x, you'll remember from your trig studies, is sine of x over cosine of x. This is a quotient identity, right? And then we can rewrite this even. We can say that this is equivalent to the limit, of course, as x approaches 0 here, of, now let's rewrite this as sine of x over x times 1 over cosine of x. Do you see what we're doing here? We're manipulating the argument so that we have something that we can work with. Okay, let me, if I can here, divide this board right there. All right, so I'm going to go to the top over here. So then this is equivalent to, let's see, what we can do here is use the product rule for limits. So to say this is the equivalent to the limit as x approaches 0 of sine of x over x, right? And that is something that we can do, evaluate, times, just bear with me for a second here. All right, the limit as x approaches 0, yes, that is the word limit there, of 1 over cosine of x. All right. Now, the limit of sine of x over x as x approaches 0, that was one of the rules we wrote down, and that is equal to 1. So the first limit is equal to 1, and the second one is equal to basically 1 over 1, because remember that the limit of cosine of x, as x approaches 0, well, first of all, the numerator is constant, so that's just going to be 1, right, by our constant function rule. And then our trig rule we wrote down is the limit of cosine of x as x approaches 0 is equal to 1. So this is definitely 1 over 1. So then this whole thing is just 1 times 1 over 1, which is just 1. So the limit of this trig expression is just equal to 1. Man, that was fun. All right, everybody. I hope you took really great notes, really organized notes. You have all of your rules clearly written. So I hope you learned a lot. Thanks for watching. See you later.